They're not with needed.
No. Yeah, Rick's gone.
Okay, the row space of a matrix is orthogonal. It's null space. We have assigned you problems where you find a basis for the null space, a basis for the row space, and show that the basis vectors in one are orthogonal to the basis vectors in the other, so that they're orthogonal spaces. Okay? So we write that as R of A is orthogonal to N of A, null space. And you can think of this as being like in 3 dimensions. If the row space is 2-dimensional, the null space is 1-dimensional. It means that the row space forms a plane through the origin, and the null space forms a line through the origin, and they're perpendicular. Or maybe the null space is 2-dimensional, and it's the plane through the origin, and the row space is a line through the origin. Okay? So this has a lot of implications. One is, if V is a vector in V,
Thanks for those Jerusalem artichokes. They were delicious. Yeah, we even roasted them for Thanksgiving. Take care, Thurl. We'll see you later.
then, hey Ben. Good guy, I can't help it, he's talking too loud next to my door. I do it too. Yeah. Okay. V's in V, where A is a matrix that maps V to somewhere. So let's just regard A as a matrix that maps V to some space W. Okay? And A is a transformation, but A is the matrix in terms of which we represent the transformation. Okay, so okay. Now, V is a sum of a vector in the null space and a vector in the row space. Okay? And Vn and Vr are unique to V. In other words, there's not another member of the null space and member of the row space that would add up to the same vector. Okay? Not hard to prove. We might look at the proof. Just assume that it's not so you got 2 of these that aren't the same, and then you easily prove that the difference of the 2 vectors is the 0 vector. Okay? So that they are the same. But maybe look at that later. I want to frame the whole idea of the least squares transformation in terms of direct sums. Okay? And I'll tell you why here before we're done. Okay, so you got these 2 vectors and they're unique to V. So there's a unique way to represent any vector in V as a sum of vectors in the null space and the row space. Another way of proving that is, okay, if you accept that you have a basis that consists of the vectors in a basis of your null space and a basis, that the basis vectors for your row space, a set of basis vectors for your row space, then this has to be a sum of basis vectors for your null space. And they're orthogonal to all the vectors in your row space and so forth, okay? So, I don't want to, again, go too deep into that. Okay, so, I'll just say this says that we write that this way. That your vector space is what we call a direct sum, a plus sign with a circle around it, of Vn and Vr. And, you know, I'm famous for using clumsy notation today. I've already got a notation for Vn and Vr. So what I was about to say is just totally redundant. So V is the direct sum of the null space and the row space. Okay, in general, a direct sum means that every vector in your space is a sum of vectors in this subspace and this subspace, and that sum is unique. Okay? So that's a direct sum any vector in your space is a unique sum one in each subspace. Okay? Now, if your vector happens to be in one of the subspaces, well, then it's that plus the zero vector from the other one, right? And the zero vector is in any subspace. It's the only thing that they have in common, okay? And from this, it's necessary that the subspaces have only the trivial intersection. That is, the only thing they have in common is the zero vector, okay? So the picture I've drawn of your vector space V, we've drawn a couple of times here. You got your row space and your null space, and they're orthogonal. Okay? And then you got all the vectors out here. If you've got any vector out here, then there's a unique vector here, and a unique vector here, such that V equals uniquely Vn plus Vr. Okay? Now, does that halfway make sense? Because if it does, you're, kind of a good ways along to understanding what we're going to do with the whole idea of least squares approximation.